Hi there, Physics 152, and welcome to week 7 of the practicals. You're now in the second half of the course, and your professor has been talking about oscillations and waves. So today I'd like you to focus on chapter 15 on the pendulum. So there's something called a simple pendulum, where you've got a mass on a light string, and then what you do is you push it up to you measure theta as being theta equals 0 when it's hanging straight down, and then theta increases. When you release it from some angle theta, it oscillates back and forth around theta equals 0. There's also something called a physical pendulum. Basically, it's the same thing, but it could be any shaped object. So you could use some sort of torque, gravitational torque, to see that this object is oscillating. My glasses here are oscillating under some pivot. But either way, an important part of the analysis of your textbook is called the small angle approximation, saying that theta max is less than about 10 degrees. If you make the small angle approximation, then the motion is called simple harmonic motion. And there's an equation you can write down for theta versus time. It's a sine wave, or you can use sine or cos. And the frequency and the period are both given by a simple equation, which is related to the square root of the length of the pendulum. So the period's longer, it's the square root of L over G times 2 pi. Okay. Now, my question is, what happens if you release the pendulum from an angle that's greater than 10 degrees? So now you don't have the small angle approximation. So it turns out there is no solution you can write down for the pendulum where you don't have the small angle approximation. It might look like simple harmonic motion because, again, it is oscillating around the center, but it's not. If you look very carefully at theta versus time, you don't get a sine curve. It's a different shaped function. Also, the period is not given by this 2 pi square root of L over G. You have to figure that out. So the only way you can analyze a situation like this is you could either build a real pendulum like this, nail polish on the end of the dental floss, which you're going to do today, and analyze it, or you can write a numerical simulation in Python. So you have the skills to do both. So in activity 1, I'd like you to build a real pendulum and attach it to some fixed point, and then take a video of its motion with your phone or something, and then read that video into the Tracker software. So if you don't remember how to use Tracker, it's a good idea to look back at the introduction video I did, I think for Practical 3 in the fall in Physics 151, to review how to import a video into the Tracker software, how to create a calibration stick. So I have a video here where you can kind of see there's the ceiling up there where there's a little screw, and then this little car which is hanging from the dental floss and swinging back and forth. So I measured that this was 1 meter, so I made a calibration stick. I also put the coordinate axes to be up at the top where the pivot point is. It's called image 6398. And then I made a point mass, and I went through and tracked, looks like about 80 points of its motion. So there's X, there's the Y, it makes X and Y. It's easier to see with X because that's the back and forth. It swings back and forth 1 time for all these points that I've made. So those are my data. Now, the problem is you want to have theta versus time, where theta is, again, that angle from hanging straight down. So the Tracker software doesn't make that. So what you're going to do is use some sort of spreadsheet to make that yourself. The way you do that is first export the data from Tracker by clicking on Export Data File. Mass A are those points that you made. All cells, that's good. full precision is fine. And delimiter tab, you can choose tab or maybe comma is easier. And then save as, I'll just call it image 6398, since that's the file that I did, .csv for comma separated values. Then I can open that file with Excel. And it looks like this. You've got time, you've got X, and you've got Y. So next, I'd like to compute what theta is. So we need to figure that out. So remembering that video, this was the little object swinging along, and I had set my coordinate axes to be up at the point where it was attached to the ceiling, where the string is attached to the ceiling. So Y was that way and X is this way. So let's go to blue now. If we look at this triangle right here, this is the X coordinate of the object, the point mass where I clicked. And then this is negative Y. So to make this a positive length, I'm going to call this distance, positive distance, negative Y, since negative 1 times a negative number is a positive number. So if this is your angle theta, theta is what I'm trying to find. I know that the tangent of theta is equal to the opposite divided by the adjacent. So x divided by negative y, or it's the same as negative x over y. So if you solve that for theta, you get theta is equal to tan to the minus 1, sometimes called arctan. I'm going to call it arctan, so that since that's the function in Excel, of negative x divided by y. Now I could type that equation into here. What I'm actually going to do, just to give you another option in case you don't have Microsoft Excel, is to try a Google Sheets. So I can take these data and copy them right in. So anyway, now we were going to do, what was it? It was arctangent, right? So I'm going to put a tan of, now there's a negative sign, so I'm just going to put negative 1 times, select the x, which is b2 in that case, and divide it by y, which is c2, and parentheses. I'm not going to do the suggested autofill yet. Does not look right. Oh, right. This is in radians. So this function a tan always gives radians. So I'm going to convert it to degrees by typing equals 180 degrees divided by pi times a tan. There we go, negative 61 degrees. So it starts off at negative 61. I remember that's where I released it from. And then Control C, and then select down, tool below it, Control V. So for every cell here, I have, for this D3 cell, that is B3 divided by C3, B4 divided by C4. So for every value of X and Y, I've now computed a theta. So now I can select column T and hold down the control key and select column D and then click Insert Chart. And this gives theta versus time for these data. And you can see it was a little glitchy there where I didn't click in exactly the right spot. You can also see a few things like I release it from, you know, as it goes, the amplitude decreases a little bit, so I'm going to have to find some sort of average amplitude. So hopefully that gets you started on activity 1. And the idea is that you will do this experiment twice. Once purposefully going for small angles, where it's simple harmonic motion, and you can check the period to be what's expected for small angles. And the second time, I'd like you to do it for about as large an angle as you can get it. Obviously, you can't go beyond 90 degrees or it falls straight down, but you can get up to about 90, or at least, you know, maybe more than 60. Now, In the case of these 60 degrees, what do you compare it with? Well, there's only one thing you can do, and that is write a Python code and try to simulate it. So we're going to try to do a numerical simulation of your data to see how your observations match what the theory predicts. So if you go on to the online practicals and click on the Quirkus, find the pendulum.py and download it somewhere. So now you have to open that with this spider. Remember the whole spider anaconda? And again, don't forget to refresh your memory if you haven't used Python in a little while. In Spider, I'm going to go File, Open, and there it is, pendulum.py. And so you can, I encourage you to read through this. So you're importing some stuff. Theta deg max equals 45 degrees. There's a conversion to get it into radians. Then it sets the initial angle, sets the initial angular frequencies. It's released from rest. There's G 9.8. I've set the length to be 1.0. You should set that to be whatever, whatever the length it is that you actually have. Time step in seconds. Initialize the time. Cross count. These are these various initials. Then you're opening up an output file. And while the cross goes on, you're printing theta. You're finding the angular acceleration by using the force divided by the mass. So the force is the force of gravity mg divided by, in the particular direction, which will give it a torque. So alpha is equal to negative g over L times the sine of theta. So we're not doing the small angle approximation. And then updates omega, updates d theta, adds the new d theta, counts how many times it crosses 0 so that you can give an estimate for the period once it crosses the 0 in the twice. Okay, so we can run that with F5, and we get for initial angle of 45 degrees and a pendulum length of 1 meter, we get a period of 2.089999, so basically 2.09 seconds. So if you have a pendulum that you maybe release from an angle of 61.5 degrees, and it has a length of maybe say 43 centimeters, you Control S that, press F5, and you get that the predicted period is 1.42 seconds for this for these parameters. So this is a way of numerically simulating. It's outputting some data into this file called pendulumoutput.csv. So if you find that, it's another comma separated value. It looks like this. So there's the latest one we did with the 61.5 initial. And so you can either, with this, make a chart, or you can read it into Google Sheets. But basically, insert chart, make a line plot or something. And you can see that for the numerical simulation, it is a very beautiful cosine curve, and the amplitude doesn't change with time and stuff. But it isn't exactly cosine. And if you really, really increase the theta degrees max to be even more than 90, you start to see it really diverge from simple harmonic motion. So that's it for today. Good luck this week, and I'll see you next week. Bye.